Good day, everyone. So today we shall be looking at the part two of our last topic, and that is alternating current. Alternating current. So the last time we had this topic, we were able to see that there are two major types of current: the DC current and the AC current. And that the AC current, the type of current that flows in one direction and reverses its direction. And then we're able to consider three major circuits that the AC current flows. And the first one was the resistance only circuit. From here now, this is one of the circuits we consider in an AC current, where you have only the resistor connected to the circuit. The other type of circuit you can have in an AC current is the capacitors only. This is the capacitor. Let us turn off the resistor. So this is capacitor only circuit, AC circuit. And the third one is where you have the inductor only. Let's turn off the inductor. Let's turn off the capacitor and turn on the inductor. This is inductor only circuit. We're able to look at the root mean square current, the root mean square voltage, the maximum the the maximum voltage also and the maximum current, and lastly the instantaneous voltage and instantaneous current for each of these circuits. Okay, but today we are going to the part two of this topic. All right, and this part two will be talking about the combination of the three in a situation where you have the inductor in the AC circuit, you have the capacitor as well, and then you have, you have the resistor as well here, and then you have the capacitor as well. In this case, what happened? So the total voltage across the whole component. What happened to the current as well? Now pay attention that these three components, the resistor, the inductor, and the capacitor, are all connected in series. You can see. So this is called serial arrangement, RLC serial arrangement. The RLC there means the R is resistor, L is inductor, and the C is capacitor. So whenever components are arranged in series in electricity, it's only one current that is being supplied to them. So the current that flows through the capacitor is the same current that flows through the inductor, the same current that flows through the resistor. Okay, so today we are considering the combination of the three components in an AC circuit. So firstly, the same current flows through, all right, but then the voltage across each of the components are different. Although this is the main supply, this is the supply of the main supply of the AC current, for example, our generator. But when the voltage supplies and the current begins to go around, the voltage across resistor is usually different from the voltage across inductor, and it's different from the voltage across the capacitor as well. So we are going to be looking at the formula for each of this one at a time. So let's dive into some of them. Okay, now when capacitor, inductor, and resistor are connected in series, like I showed us in that diagram, the maximum current obtained, usually they are the same, but it's calculated as maximum voltage, where the I naught represents maximum current, V naught represents maximum voltage. So the maximum current in that circuit, or peak current as well, we call it either peak current or maximum current, equals maximum voltage or peak voltage over Z, where the Z represents the impedance. Impedance simply means the total resistance offered by the three components in the circuit. The total resistance by each of them equals impedance. So that's equation 1. Another formula we need again in this RLC circuit is the root mean square current. The root mean square current is actually the effective current in the circuit. We talked about it the last time. So by formula, it's also equals the root mean square voltage over total resistance, which is called the impedance. Now the impedance itself by formula will be square root of the square of resistance plus into bracket difference of inductive reactance and capacitive reactance all square, and then you square with everything. So if you want to determine the total resistance offered by the three components, this is the formula you use. And then the voltage supply, this is the circuit here now, the one I showed us, this is the circuit diagram. This is the resistor, this is the inductor, and this capacitor. Okay. Now, like I said earlier, the voltage being supplied usually split whenever it's in series. So the voltage across R is VR, the voltage across L is VL, and the voltage across C, which is capacitor, is VC. So now, if you want to now get this Vs, which is the supply voltage, by formula, supply voltage square equals to VR square plus difference of VL and VC all square. Okay, so this is how to determine the supply voltage by formula as well. This supply voltage that we have here. Okay, now last part we've already talked about VR being in phase with the current supply whenever it is only resistor. We talked about this last time, so you can check the last note or the last video. And also, whenever we have inductor connected in an AC circuit, the voltage leads the current, or we can say that the current lags the voltage. We use them in a reverse manner. But whenever you have only capacitor in the AC circuit, the voltage lags the current, or the current leads the voltage. So these are very important things that we need to know. But there are situations where we can decide to connect just two of the components. For example, if I choose to take away the capacitor, now I have the inductor and the resistor. In this case, now what happens? What will be the total resistance offered by the circuit? Again, when I decide to remove the inductor and include the capacitor, so we have the resistor and the capacitor. What will be the total resistance in the offered by the circuit? Now, to do that, we already said whenever you have the resistor and the inductor, the total voltage supply, of course, still remain VR square plus VL square. Okay, but whenever you have the resistor and the capacitor, the total voltage supply still remains VR square plus VC square. Now, in terms of total resistance, which is Z, if it is only resistor and inductor, that will be, we have a total resistance to be R square plus SL square, where the SL represents the inductive reactance, and the same apply for capacitor too. So all these formulas are very important for us to know. Now again, the total voltage by graph is drawn like this. Okay, it's drawn this way. So here you have the inductive voltage, or the voltage of the inductor, to be pointing the arrow upward, while the voltage of the capacitor to be pointing downward, and the voltage of the resistor is pointing at the right hand side. Now the supply voltage by formula is now what we obtain in this equation here. All right, and now there's what we call phase angle as well. Okay, we talk about voltage leading current in an inductor, and also voltage lagging current in a capacitor. Now the phase the vector diagram, or what we call the phasor diagram, is this. Now this first one is when you have only the resistor connected. You can see that both the voltage and the current are in phase. So during the phasor diagram, this is how you go for it when it is for resistor only. When it is for inductor only, the phasor diagram or the vector diagram is difference of 90 degrees. In this case now, the voltage is leading the current, all right, by the difference of 90 degrees. All right. Now, the phasor diagram for capacitor is this. In this case, you can see that the VC is pointing downward. That's because the voltage, whenever it is lagging, it's pointing downward. The voltage lags the current by a difference of 90 degrees. Okay, so this is called the phasor diagram. The phasor diagram just shows us the visual representation of this observation. Okay, so having said that, I think we need to move on and see an example. So we say find the root mean square value of an alternating current whose peak value is 5 ampere. So here we are given the root mean square value to be the unknown. Okay, we have to find it. So IRMS is unknown. Peak current is given, which is I naught to be 5 ampere or maximum current. Now by formula, the root mean square current is peak current over root 2. And then when we simplify it, we have our value of the root mean square current to be 3.5 and 3.54 ampere. Okay. All right. So let us see another example. In an AC circuit, the peak value of the potential difference is 180 volts. All right. So in this case now, V naught, the naught always represent the peak or maximum. So the peak voltage now is sometimes we call voltage potential difference. It's 180 volts. So what is the instantaneous potential difference when it has reached 1/8 of a circle? Okay. So we know that one circle is 360 degree. So 1/8 of a circle definitely will be 360 over 8, which is 45 degree. And this degree is product of W and T, or the angle itself. So by formula, to get our peak voltage, to get our instantaneous voltage, by formula, instantaneous voltage is equal to peak voltage sine WT. Our peak voltage will voltage to be 180. So 180 sine, our WT is 45, sine 45. And when you simplify this by short form, you will have your answer to be 90 root 2 volts. Okay. Another example here, it says a circuit consists of a resistor of 500 ohms and a capacitor of 5 microfarad connected in series. If an alternating voltage of 10 volt and frequency 50 Hz is applied across the series circuit, calculate the reactance of the capacitor. 2. The current flowing in the circuit. 3. The voltage across the capacitor. And B part, this is A part. The B part says if the capacitor is replaced with an inductor of 150 millihenry, calculate the impedance and voltage across the inductor. Okay, so let's write our parameters out. So we are giving resistance to be 500 ohms. We are giving capacitance to be 5 microfarad. We are giving the voltage to be 10 volts. Okay, that's the voltage is 10 volts. We are giving frequency to be 50 Hz. We are giving inductance to be 150 millihenry. Okay, it's given there in the question to be 150 millihenry. All right, and then we have to look for the capacity. We have to look at it. We have to look for the first one. Okay, we are also supposed to look for the current flowing in the circle. That's I. We have to look for the voltage across the capacitor. That is our VC. And then the second part of the question, that if the capacitor is now replaced with inductor, then we have to look for inductive reactor and then the voltage across the inductor. Okay, so these are the things given to us in the questions. All right. Now, having said that, now let's go ahead and solve the problem. Now, by formula, capacitive reactance is 1 over 2 pi Fc. So, of course, we are given our F to be 50. Our C is 5 microfarad. So when you substitute the values here, the capacitive reactance will be 636.62 ohms. So we solve the I part. So the II, which is the current in the circuit, for us to get the current in the circuit, we need to get the total resistance in the circuit, which is impedance. The impedance in the circuit will be square root of R square plus capacitive reactance square. Our R is given to be 500, so we square that. Our AC we've obtained to be 636.62. We square that, and when we simplify this, we have 809.5 ohms. Third question says we should get the voltage across the capacitor by the current in the circuit rather cannot be obtained by using I equal to V over Z, because we will obtain our Z to be this value and our V is already given in the question to be 10. So we substitute the value. We have 10 over 809.5, and that will give us the current flowing in the circuit. That's for the second part of the question. Okay, now I won't say that we can now go on to solve the third question. And the third question says we should calculate the voltage across the capacitor. So to do that, to solve that, we just use the formula VC, that the voltage across the capacitor is equal to current times capacitive reactance. The current has been obtained to be 0.124. Then the capacitive reactance, we've obtained it earlier to be this. Then the product here will give us 7.89 volts. So that's the voltage across the capacitor. Now the B part said if the capacitor is now replaced with an inductor, we should calculate the impedance and voltage across the inductor. Okay, now the same way we solve the first one, very simple. So we need to use the formula for inductive reactance, which is SL equals to 2 pi FL. Okay, so inductive reactance is 2 pi FL. Our F still remain 15 in the parameters we have. Our inductance, which is the L, is 150 milliampere. And when you simplify, the inductive reactance is 47.12 ohms. Okay, so we calculated the inductive reactance, but then we have to calculate the impedance. We have to calculate the impedance and voltage. Okay, now the impedance now cannot be calculated using the formula. You could see using the formula Z equals root of R squared plus SL squared. Our R is still given as 500 in the question. Our inductive reactance we have obtained to be 47.12. Simplifying this, we have 502.2 ohms. Now we've solved that part, the impedance. Now the voltage across the inductor will now be using our formula also. But before we can do that too, we need to also obtain the current flowing in the circuit now that we have replaced it with inductor. So the current still remain voltage over Z, and our voltage is 10 in the question. Our Z in this case is now 502. So the current this time around, since there is a replacement with inductor, is 0.0199 ampere. Now to not get the voltage across the inductor, we just use the formula VL equals to ISL. Okay, why the VL is the voltage across the inductor, the I is 0.199, which is this, times the inductive reactance, which is 47.12, and finding the product of this, we have 0.938 volts. Okay, so that is just an example on how to solve problem in RLC series circuit. Now, there's also what we call power, the electrical power in an AC circuit. Now, the average power, which we sometimes call the root mean square power, is equals to IV cos phi. Okay, where the cos phi is now the power factor of the device. Of course, the I is the current, the V is the voltage, big is the average power. Okay, by formula, power factor, which is cos phi, equals to R over Z. So now whenever the power factor is 0, whenever we obtain our power factor to be 0, that means if cos phi equals to 0, it means that it means that either the inductor has a pure reactance, or the capacitor has a pure reactance, okay, or pure inductance or capacitance. That's what it means whenever we have it to be 0. And what that means is that there is no resistance in the inductor or the capacitor. Now, by formula again, another formula for power is P equal to I square R. Whenever the circuit has a resistor, this is the formula we use. Okay, to obtain instantaneous power, we use P is equal to IV. Okay, so that's it. Now, having known the formula, let's see an example on this. A series circuit consists of a resistance 600 ohms and an inductance 5 Henry, okay, and an AC voltage of 15 volts, that is good mean square voltage now, and frequency 50 Hz is applied across the circuit. So we have to calculate the current flowing through the circuit, the voltage across this inductor, the phase angle between current and the applied voltage, the average power supply, the potential difference across the resistance. Okay, so we have 5 problems to solve here. Alright, so the parameters have been written. Resistance is given to be 600, inductance is 5 Henry, root mean square voltage is 15 volts, frequency is 50 hertz. We have to look for currently that's the first one. Second one, we have to look for voltage across the inductor. Third one, we have to look for the phase angle. Sometimes we call this phase angle the phi. We have to find the power and then the voltage across the resistance. Okay. Now, having said that, for us to solve the first one, we need to obtain the total resistance in the circuit, which is the impedance. And in impedance formula is root of R squared plus SS squared. So our R is 600 as given in the question. Our SL, we've already obtained it here. SL by formula is 2 pi FL. So F is 50, L is 5. Simplifying it, we have 500 pi ohms. So if we substitute it here to get our Z, we now have our Z to be 1681.5 ohms. So to get the root mean square current, which is the first current now, the current flowing in the circuit, will now be root mean square voltage over Z. So root mean square voltage is given in the question to be 15, and we will obtain our Z here to be 1681.5, and then our current there will be 0.00892 ampere. Okay, now the second one is for us to get the voltage across the inductor. By formula, voltage across the inductor will be ISL. So I have been obtained to be 0.009892, and our SL is already obtained here to be 500 pi, and then simplifying we have 14.01. All right. So I won't say that we have to also obtain the phase angle between the current and the applied voltage. So to do that, we use our formula. Okay, the phase angle is the phi. So tan phi rather is equal to SL, that's the capacity reactance over R. Okay, that's the formula for phase angle. Now SL has been obtained to be 500 pi. Okay, we've obtained this value here, and then R remains 600. Then we have our tan phi rather to be 2.62. And when you find the tan inverse of 2.62, our phase angle will be 69.1 degrees. The next question says we should find the average power supply. So the average power supply by formula is P equals I square R. So our I, we already obtained it earlier here. And then our R is already given in the question to be 600. So simplifying that, we have 0.05 watts. The next question says we should find the potential difference across the resistance. Of course, that will be VR, which is the potential difference across the resistor rather, is equal to IR. Our I still remain, I will be the same thing since they are in series. Our I still remains the same value, which is 0.00892, then times R, that will give us 5.35 volts. Okay, so that's it. So another example before we look at that is let's look at resonance in series resonance in RLC series circuit. So resonance is said to occur in series in RLC circuit when the maximum current is obtained in that circuit. So when we have maximum current obtained, then we say resonance has occurred. Also, we can say that it occurred whenever the capacitive reactance equals the inductive reactance as shown here. So this is when we say that resonance occurs whenever SL equals SC rather. Okay, resonance occurs, and then the maximum current is obtained and the impedance is at minimum. So by formula, the frequency obtained when there is resonance is equals to 1 over 2 pi root LC. Okay, that's the formula. And also the angular frequency is 1 over root LC. And then we use this resonance because of resonance occurring. That's why we could tune our radio and we could hear what is happening in our radio and in our TV station as well. There's a lot of resonance that is occurring in an AC circuit. All right, so let's see an example on this. An AC voltage of amplitude 2.0 volts, all right, is connected to an RLC series circuit. So if the resistance in the circuit is 5 ohms, and the inductance and capacitance are 3 millihenry and 0.05 microfarad respectively, calculate the resonance frequency. Okay, so two, we have to calculate the maximum AC current at resonance. So in the question, we are given the peak voltage, okay, to be 2 volts. Whenever you hear amplitude, so this peak can also be called maximum, it can also be called amplitude. So peak voltage is 2 volts. Then the impedance is given to be 5 ohms, as you can see here. Okay, that's the resistance of the circuit now. Okay, then the inductance is 3 millihenry, capacitance is 0.05 microfarad. We have to find the resonance frequency. Okay, and we have to also look for the maximum current or the peak current or the amplitude of the current. So resonance frequency is this formula. Okay, so the frequency we obtain when there is resonance is called the resonance frequency, and we have seen the formula earlier. So we just substitute our value of L and C, which is here, and then we have our resonance frequency to be 12,993.43 Hz. Then to get the peak current, we use V maximum voltage over Z, which we have it to be 2 and Z to be 5, and then we have 0.4 ampere. All right, so this is where we shall be drawing the curtain today. So till I come your way again, do have a wonderful day.